All right. So we are finally starting the Nand2Tetris series in earnest. um, so what we're going to do today is kick off the project with a bit of planning. First thing we'll want to do is build an emulator for the Hack hardware platform. But zooming out a bit, so what Nand2Tetris is going to be um, is building it. So it's building a full computer from first principles, right? So I'm following along with the book, The Elements of Computing Systems. And in this book, you start with NAND gates, build some logic circuits, build up eventually to like an ALU and a CPU, and memory, I/O, yada yada. So like a full architecture for like a computer platform. And on top of that, you implement a machine language, an assembler, like a VM translator, and then a compiler for a program that runs on that VM, which then runs on this architecture. So the last few streams I did was doing this game MHRD Micro Hard, and it's basically I was doing this as a warm up. So this is basically just using a hardware definition language to write up all the circuits, so connecting a bunch of chips together into bigger chips, and then eventually making a full CPU design. So we did that as a warm up, but now we're going to do basically um, something very similar to this, except we're going to be writing in Scala an emulator for that platform. So I have in front of me here this book. This is the Elements of Computing System. So I'm going to go reference this um, as we move along. And if we add anything else, we might add other things. So I've done this before. I did this like over a decade ago. So this is an opportunity to like tinker around with it and play around a bit more and not just, complete the projects like the assignments at the back of the book or whatever, right? Um, yeah, so I want to build an emulator. I want to have it run in the web. I want to add some visuals, be able to like pause, rewind, step one at a time, maybe do some like performance enhancements so I could fast forward or save states. I don't know, whatever you might want to do in the emulator. And then build other stuff on top of that. This is going to be very open-ended. The point is to be able to explore and just have fun with whatever extra rabbit holes you might want to go into. Um, so that said, let's think about the components that an emulator will need. So I'm starting so much from scratch. We haven't even built up initiate a project yet. So we're going to do SBT new and initiate a project. We get to see everything. um, I'd consider doing all the planning offline and just coming to you with a plan, but I think it might be more honest just to do all the planning on stream too. I figured someone might appreciate that. If someone ever wants to just see all what happened, I can make edits of these live streams. But this is here, so it exists. It's in the archive. Um, yeah. So Scala, we want Scala 3. Failed to load, what? Um, Seems to have worked. Nand2Tetris. Okay. Sure, let's make it main. Git branch and change the default. Okay. And what do we have? Let's just commit all of this actually. And from SPT2. Cool. Um, okay, so they start us off with a main and a test suite. Let's open that up. Actually, I think what I want to do here is have a doc. So we'll open up main, but what I really want to do is have a little planning doc, and maybe I'll whiteboard a little bit. So already open-ended. Um, uh, yeah, let's mess with the README here. We can make this our planning doc. Okay, emulator planning. Okay, so at the end of the day, there's like, oh, what is up with that? There's a few things I want to be able to do. So we want something that can just run the binary code. So run compiled hack binaries. I think we also want we'll also want an assembler because I we don't want to work just with binary. So in this part in this arc, what we're building, I think we want to primarily work with like handwriting assembly. So assembler from ASM to binary. And for this, I do want to have something more semantic, right? So like normally with the binary, like that would go straight to this to like the computer platform, which in itself would have like a decoder or decoding instructions, right? And figuring out like what instruction to run and whatnot. Um, but that's not where this is going. So this instead, we'll have to decode um, into our own kind of representation. So we need a representation. Um, yeah, we want a representation within Scala because we don't want to just be passing around by like binary. What do we call this? We need like a machine language representation. Okay, so well, basically, then, so I guess we assemble two binary. The thing is, I probably don't really want to write assembly either. So, like, what if I had my assembly SM as a Scala DSL? Like, maybe I could output it. Option to output text .asm files. Yeah, like if we can, I want to be able to cross-verify this against existing compilers. So whatever my assembly representation is, if I'm playing with one with some sort of AST within Scala, I should be able to pass that forth to another assembler and compare the results of that assembler. In fact, I could probably compare it against my old one and see if we get the same machine language. Of course, at some point, I probably might add optimizations or something, so that won't always be the case. But like, be able to run it through two different assemblers. Uh, so we want a Scala representation. So Scala DSL or representation, and then we want a machine language representation. And interestingly, this brings up a question like, do we go from the assembly representation directly to the machine language representation? Like we still want to run actual binaries. So I think that's something we could do, but probably shouldn't. Go directly from ASM rep to ML rep. I'm gonna start calling machine language just ML. So probably go to binary first. All right. Right. And as far as like what to, well, okay, there's a whole computer architecture itself. So there are these pieces we need computer architecture. So that is what like the IO, um, importantly memory, state of the registers and program counter, etc. In fact, let's go to the book and it should tell us like the pieces we need. So, oh yeah, I guess there is ROM and RAM. Um, so there's ROMs, there's RAM, IO, registers, slash the program counter. Um, the ALU is not like something we need to model. But I guess we need to like model the capabilities. Like same with the CPU. So like the CPU is what we're emulating here. I guess it's CPU along with the memory. Okay. Yeah, so if we're doing this, I think what I would want to do is start probably at the level of the assembly, model its translation to machine code. Um, that way, we're not just like testing with machine code or just testing with binary as we're building the computer architecture, but we can test kind of directly from assembly, right? So run some assembly, or at least maybe this machine language representation. So if I build this ML representation and then a way to uh, compile that to binary. So the steps, one sec. All right, sorry about that. Okay, so steps here. I think what I want to do then is start um, with an ML representation. And actually from there, I can go in either direction. I could go to implementing, well, maybe we do that. And I suppose we can test directly with that ML representation. So there's no need to do the assembly just yet. But that is an option. Like I could go from assembly and write a little program from assembly and test that against texture. But for making this first version of the computer architecture look fast and simple, maybe one is an representation, two some texture, state, yeah, cover the state, and then assembler, and then at some point we go to like visuals and like emulator features, something like that. Visuals, yeah, those are like rough big steps. Okay. Well then, let's start. Um, yeah, let's start by looking at the machine language spec. So there's this main. I don't think I think we want. Let's make some sort of package structure. So um, let's do like machine. Let's just have a package for machine language on its own, and then in there can be like modules for like to binary or like parsing from binary, I suppose. Yeah, because in our running emulator, we don't really want to mess around with binary. We're going to mess with our own ML representation. So we need to be able to parse from binary. Yes, I guess first step is a binary parser. Okay, so what are we going to call this package then? Um, I guess we just call it ML. Uh, Maker and touch that. Yeah, and we'll just put everything in there for now, and we can figure out as we go how we're architecting this. Okay, and then Tetris, I don't know. Um, all right. So let's look at the types of commands we have. Um, okay, there are A instructions and C instructions. Where is this discussed? The implementation of the hack CPU entails building a logic gate architecture capable of executing. Yeah, so we're not doing logic gates. I think actually that here, machine language, is in a different chapter. Well, actually, let me just check again because I think there was something in there I wanted to see. Chapter 5, 5.2. Okay. 16-bit von Neumann machine, yada yada. Two separate memory modules, instruction and data, right? So ROM and RAM. Two I/O devices, a screen and a keyboard. Okay. ALU, three registers, data, address, and program counter. Right. Um, Here, A instructions, the 16 bits of the instruction are treated as a binary value, which is loaded as is into the A register. In a C instruction, um, control bits that specify various micro operations to be performed on the ALU. Okay, yeah, so we do go to chapter 4. Hack machine language specification presented in chapter 4. Hardware elements. There's a processor, there's the registers, here's the languages. Okay. Oh, so Right, so they can already be written in two alternative but equivalent ways, binary and symbolic. Okay, so what I'm implementing then is the symbolic version, and we're gonna write a parser from the binary into symbolic. So for example, consider the abstract operation set R1 to value of R1 plus R2. Okay, so like we'll have an example directly in here. So that would be written as R1 equals R1 plus R2. Well, we can decide to represent the operation using 101, 011, and registers, and the registers using these two codes. Sure. Is that necessarily how we're doing it? Um, do I have my behind? Oh, give me a sec here to play with my. Okay, maybe that helps somewhat if I'm sharing. I'll tweak it for the next stream. Um, okay, but our language specifically, instructions. Okay, a set of registers, R0 through R whatever. This seems to be describing more registers. I thought there was only the data, address, and program counters, but this seems to be describing potentially more. See, R0, R1, R2. I don't remember. Okay, here's some instructions. So load R1 17, value of 17 into register 1. Load R2 for add. Okay. This translation is done by a program named assembler. Wait. Is this the assembly? Is this the assembly language? I might want to check. I might want to check if what this actually is the assembly language. Let's pull up our README. Um, so my rough plan is sort of there. Okay. Load A 200. So like load the address 200 into A and add A1 50 times. Sure. Okay, the hack machine language specifically. Here we go. Okay, so they were just generically talking about theoretical machine languages. So the hack machine language. Um, Hack platform uses two distinct memory units, a data memory and an instruction memory. By the way, I'm not sure how legal it is for me to like show the book here. I know like part one is essentially free online and part one encompasses like all the hardware stuff. So maybe I'll rethink things when I get to part two. But in here somewhere is the spec I'm looking for. Data memory, instruction memory, registers, address, and a data register. Cool. And they're denoted A and M. Or wait, denoted D. And a selected data register noted M. Wait, selected data register. Three 16-bit registers. A data register is D. address register is A. Selected memory register M. M is memory. So M is like whatever A is referencing. It's just A dereferenced M. B equals M, M equals D plus 1, etc. Okay, those are the kind of things we're going to want to be able to implement. The role of the data register D is straightforward. It serves to store 16-bit value, yada yada. A is address and data register. If you want to store a value in A, so this at 17 lets us store a constant directly. This is the only way to get a constant into the hack computer. So if you wish to set a D register 17, we do at 17 followed by D equals A. Okay. So we'll need to like give names to these kinds of things. And basically, at some point, I want to enumerate all the things that are possible. I know somewhere in here there is like a breakdown of a machine instruction. It has multiple parts. So we'll get there soon and then be able to start modeling that. So the hack instruction sets a, yeah, okay. So this is also talking about the M register, makes the RAM register whose address is XXX available. It makes the value available. So like M is kind of like a virtual register, or like, yeah, I mean, technically there's a register in the RAM, but like it's a dynamic register. But there's not like, a register just for M. Setting A to some value has a simultaneous effect of preparing the stage potentially for one of two very different subsequent actions: manipulating the selected data memory register or doing something with the selected instruction. Oh, right, because it points to both the ROM and the RAM. So it could mean like this is the address in ROM with the next instruction, or it could mean do something with this stuff in RAM. And so then the M register will always refer to what's in RAM. Yeah. That becomes the selected instruction. Okay. So we'll need to have, let's go back to our notes here. So RAM, program, registers and program counter. Let's list all the registers. So there is, there's the A register. There is the D, there is M, and there is the current instruction. PC, and then like the value of the current instruction. Like, okay, these aren't all registers, but the point is that these are all elements of the current PC state. Yeah, those are the elements of the state that we're going to be modifying. Well, like M is not something we modify directly. So like PC we modify directly, but like these are kind of what's the word? Derived. Okay. Is that big enough to read? Let me know if anything here is too small. I can make him bigger. Um, Great. So that's our registers. And the hack instruction m equals 0 sets RAM register 0. Okay, yeah. It sets the value in m. Branching. Okay, right. We can jump around. In hack, this is done by at 29 followed by hack instruction jump. Wait, 0? Semicolon jump? What's with that? The jump is a specific command you could get. And if I remember correctly, like there are variations of jump within like the machine language itself. So like jump greater than or less than. Unconditional branching. We'll explain the 0 semicolon prefix later. Okay. Since the ROM is assumed to contain the program we're currently executing, start at address 0, then two instructions end up making the value of ROM 29 the next instruction to be executed. Right, because we jump to the address in the A register. Go to execute the instruction address by the B register. Okay. And there's conditional branching. In this case, D semicolon means evaluate D. So I guess that was like evaluate 0, which is a way to say like do this unconditionally. Okay. To recap, the A register serves two simultaneous like different addressing functions. Following, an at instruction will either focus on the selected data memory register M and ignore the instruction, or you focus on selected instruction and ignore the selected data memory register. This duality is a bit confusing, but note that we got away with using one address register to control two separate memory devices. Yeah, it's cool. It is a super minimalist this architecture. That's something I like about it, which also gives me pause to like extending it. If I extend things, it'll only be for performance because I don't know, because I'm trying to run this whole thing in the browser while keeping it like functional and like making the state rewindable and whatever. I don't know. It might be. Let's see. Okay, let's page ahead. Variables. There's variables in the machine language. The XXX in hack instruction can either be a constant or a symbol. If it's at X where X is symbol bound to some value, the instruction sets the A register. Wait, how can machine language itself have variables? Shouldn't that be at the assembly level? Is this assembly? This is assembly. Maybe I should just be implementing assembly first. Yeah, I should probably just straight up start with assembly. And as it's necessary, like as I'm translating that to machine language, then create like a symbolic representation of the machine language for myself to like work with as I'm powering the actual state transitions. Okay. Um, select the RAM register. A high level assignment statement like x equals 17 can be implemented as like at 17 d equals a, right? And then we jump to at x, and x is a symbol. Okay, x is a symbol like a place in memory. Right, so if we decide that x lives at 513, then x at x moves our puts its address in a register, and m equals d saves whatever was in d to a. So that is like a lot of steps to do a simple thing. Like a different architecture would probably be able to do that in just like one step. Um, like it's maybe pause and consider like maybe I want to do an emulator at like a VM layer instead of like the computer platform layer. Maybe like for performance, if I'm running anything like super complicated at the highest level. But I don't know. Still, thanks to assembler, variables like x can be named and used in hack programs at will and as needed. Suppose you wish to write code that increments some counter. One option is to keep the counter in, say, RAM 30 and increment using the instruction at 30, do m equals n plus 1. That's pretty legible. A more sensible approach is to use at count m equals n plus 1 and let the assembler worry about where to put the variable in memory. Right. Yeah, we do variable names. Yeah, when we write the assembler, we'll have to have like a symbol table that maps all of these variables to like actual addresses. Don't care about the specific address as long as the assembler will be able to resolve the symbol to that address. Um, yeah, chapter 6, which is maybe actually where we start tonight. But we'll see. We'll see. I still want to see deeper into the machine language specification itself. The hack language features 16 built-in symbols in R0 through R15. Okay, so these are just the values 0 through 15. And what's that used for? We'll end up saying RAM 3 to... Okay, so like the first 16 registers, I see they're virtual registers. So the first 16 RAM registers are virtual registers. I might want to model that explicitly. I mean, how we model it doesn't really like at the end of the day, we're not going to model like individual registers and logic gates and whatnot. So performance is all in our hands there. But it's interesting to think about how you might optimize access to the virtual registers in the physical architecture itself. Okay. Anyway, before we go on, I suggest you review and make sure you fully understand the code examples shown in Figure 4.3, some of which we already discussed. Okay. Let's take a look at that. Can we make that bigger? Mm, Can I view this image? There, Windows has like a built-in zoom, right? Let me just look that up real quick. Windows logo plus sign. That's it. No. Oh, okay. Yeah. Oh boy. All right. Is that more legible? I don't know how well that works. Um, but we'll run with it. Okay, so what I'm seeing on my screen, I don't know if you're seeing the same thing. What I'm seeing, we have memory access example. So D equals 17, set the data register to 17. We just do at 17, which sets A register to 17, then D equals A. Because at 17 is the only way to get a constant into any register, you have to start with the A register. Okay. Um, RAM 100 equals 17. So add 17, save D to A, then we go to add 100 and we set M to D. M being RAM location 100, that register because A is 100 is currently in A, and setting the value to D that we had saved earlier. Yeah, a little bit roundabout. You have 4 cycles to do that. And then RAM 100 equals RAM 200. Same kind of thing. Okay. And a branching example, go to 29, is at 29 and jump greater than. Sure. If D is greater than 0. Why is it? Yeah, I'm going to want to understand what's on the left side of that. But this is the assembly. This is the assembly. So this isn't the machine language I'm hoping to have like a representation for. But I think it might still be worthwhile to have like a representation for the machine language itself that is distinct from the assembly. Because again, we don't want to be passing binary around. But who knows? I might change my mind as we go. Variable use examples. So x equals -1 at x. Let the assembler figure out where x is. Yada yada. Same with count. M equals m minus 1. Sure. I think with the like that, you can do like -1 or +1 as far as like inline constants. Anything bigger, and you have to do the jumping around or like putting it into the A register and doing like m equals m minus a or whatever. Sum equals sum plus x. So at sum, d equals m, which is a value in memory. Okay, and we go at x, d equals d plus m. So d was currently sum, m is now also y at x. Oh, x is the value, right? So when we're saying d equals d plus x, we're saying the d register, which had the value x formerly, gets to be like x plus m, which is the saved value from sum from earlier. No, m is actually the x value. D is the saved value from earlier. And then at sum, m equals z. As a final step, we have to go back to the sum memory, sum location, and then set the value to d. Okay, yeah, I think that's pretty understandable. Yeah, I'm not sure you were able to see the zoom, the same kind of zoom that I did. But hopefully, I don't know, hopefully you're able to squint. If I'm editing this video in the future, I'll just take that and blow it up so that you could see. Sparkly, how's it going? It, it's going well here. So starting off with planning for the emulator we're gonna build. And yeah, looking over the spec, I'm gonna look at 2 parts of the spec. One is like the machine language itself, and another is the assembler. So at some point, we have to have an assembler turn assembly into binary. At some point, we have to have the ability to execute the binary, which means at some point down the line, we're also going to have like a state for the computer and be able to like modify that state based on the binary. But that means I'll also have like symbolic representations of all of these. So I think I'll have a symbolic representation of the machine language. And I might start by implementing that, then testing that against like a little dummy architecture, seeing if I can do the state transitions off of that. Or I might start at the assembly level and first see if we can convert the assembly down to machine language to like our intermediate representation. It depends on like how well specified or how well like named the machine language here is, whether I start with the machine language itself or the assembly language. So assembly does like have more capabilities technically. But still, that means I'm going to have two different representations in Scala for this, because I don't want to be passing binary around directly. So we'll have like a parsing of the binary, and that parsed version of the binary is what we're going to run through the state transitions. But yeah, at this point, gathering data, I figured I'd just like show the whole process rather than like um, doing everything behind the scenes beforehand, just as all in the record. Okay, so they've got a program example here. Man, I really want to make that bigger. I'm realizing maybe like an ebook's not the best format for this. I'm giving this a plus. Clicking on this image doesn't do anything. Nand2Tetris doesn't hold your hand through this. Um, it it would, but so part one of Nand2Tetris, they have you building everything in gates and circuits, right? So I'm doing a whole emulator for part one. So this part isn't really explained uh, in the book. I mean, the machine language itself is explained, um, but this isn't what you normally implement when you're going through Nand2Tetris, right? Normally, like they provide you an emulator, and they're like, "Here, you can run binary on this emulator." By the way, this emulator is exactly the uh, all the chips that you wired together earlier, right? So we're doing like a simulation of all those chips. Well, no. We're not doing a simulation of all the chips. We're just doing an emulator for the computer state. And that's the bonus step that we're doing. That's not normally part of Nand2Tetris. Um, yeah. And they also have like a VM emulator, if I remember correctly, and like other, you know, they also provided you like a visual of your um right, like you can compile your program in all, but you run it under emulator, which shows you the screen and the input. Um, and that's another part I want to build myself is like the display as well as like the I/O. I want to put all of that in the browser. So that's a part I'm going to be building myself as well. That would also normally be provided for you. Yeah, side quests. Side quests, or what's the word? What's the word when you go through a game again, but you do it on hard mode? We're doing Nand2Tetris hardcore mode. Maybe not hardcore mode. I think that means you die. You're just game over, right? Um, what is in a Zelda game? There's like a master mode after you finish it the first time. Oh, hey, look here. This is what we're looking for. 4.2.3, the hack language specification. Um, there is this pseudocode. Oh, there's this translation from pseudocode into hack assembly code. I'm going to remember that this exists, but not look at that right now. Um, and this figure 4.5, I really want to make this bigger. Let's see. I'm just going to screenshot that. I'm going to paste it to my whiteboard, and then I'm going to zoom in the whiteboard. New Game Plus. Oh, yeah, right. It's kind of a New Game Plus in that, like, I am playing the game again, but supposedly I know everything. Like, I have the unlocks. Fun fact, it was Chrono Trigger that introduced that. One of my favorite games of all time. Okay, great. This is how we're going to zoom things. We'll put it in the whiteboard. So I'm going to leave that visible for everyone else to digest. I'm going to use a bathroom and come back. Hey, thank you. Thank you for catching that. All right. Um, okay, as I was saying, thank you. Thank you for catching all of that. I need to have like a big you're on mute when I come back on my screen so I can see that. But yeah. Um, so we have A instructions, we have C instructions. It looks like there's a symbolic in the binary version. The thing I was saying about the C instruction here, by convention, this second and third bit don't really do anything. So it's like by convention, we just default them to 111. I think if we ever want to extend the binary language, this is where we might do it, right? Like maybe 110 allows us to include like a multiply instruction or something like that. But this is what we can model directly as our like machine language representation. Um, so we could have different case classes. So I'm going to jump ahead to this D and the J because those are easier to understand. So like these 3 bits would represent a destination. So either to RAM, to the D register, to the A register, or some combination of all 3 of those. Um, yeah. And then likewise with jump, um, some combination of less than is allowed, equal allowed, or greater than allowed, and then up to like an unconditional jump. So what I could do is like bit shift these when I'm parsing. Use the first 3 bits to parse our jump, next 3 bits to parse our destination, and then these 6 bits represent our computation. And I think we have to go to a different chapter for what that computation means. But these basically are the control bits for the ALU. Hey, good to see you again. It's been a hot minute. I look totally different. Well, let's see. My hair's down. I did get it cut, so it was getting pretty long. It'd been like a year since I'd gotten it cut. I don't think I'm always shaven. The reason I shave actually is because when my hair's down like this and I have a beard, it's like Velcro. Like my curls just stick to my stick to my beard. So if I had my hair down, I have to shave my face. It's like a disguise. Static shock. Oh yeah. Maybe one day I'll do locks of some sort. But I've never done that. Never done braids or anything. Okay, so this is what we need. This is what we want to represent first. But let's go back to the book. What else does it have to say? So it goes into more detail into like what the A instruction is, what the C instruction is, the computation specification. So an instruction, a C instruction has as part of it a computation specification. What is this A bit though? This A bit is like a variation. It's like, are we doing and or no, hold on. A minus 1 versus M minus 1. Oh, I think, are we referencing memory or are we directly messing with the registers? So let's jump into this and try to understand the difference between the two data columns. Um, so for comp 0, what even is the second column? Okay, I'm gonna straight up just read what it says. Swap these two around. Okay, computation specification comp. The hack LU is designed to compute one out of a fixed set of functions on 2 given 16-bit inputs. Yeah. In the Hack computer, the two ALU data inputs are wired as follows. The first ALU input feeds from the D register. The second feeds from either the A register or from M. Okay, so that's what this A means. When A equals 1, we're feeding in the second input from memory. When the A bit is 0. Okay. And the selected data memory register when the A bit is 1. Great. Taken together, the computed function is specified by the A bit and the 6 C bits comprising the instruction's comp field. So this 7-bit pattern can potentially code 128 different calculations, of which only the 28 listed are documented in the language specification. So most of these are undocumented, probably because it doesn't make sense to do them. Suppose we want to compute the value of the D register minus 1. Okay, so according to figure 4.5, that's this one here. According to 4.5, it's going to be done using the symbolic D minus 1. Okay, D minus 1. And these are control bits to the ALU. I forget what they mean, but we can look them up, and I'll paste that in here too. But in this case, it doesn't matter whether A is 1 or 0, does it? Right, so A equals 1 or A equals 0 is the same command. So there are multiple ways to encode then the action D minus 1. And I think I'll stay honest to this, and when I'm modeling this, I'll keep that in, whether it was referencing memory or not. Maybe I'll have a normalization step afterwards. Just maybe I'll find some use for that. Okay, so um, so there's this instruction D or M. So I think this here is what the assembly actually looks like. Right? You could write something like D equals D or M, but we're not going to implement the assembly today. And then the destination, okay, we just went over this. I don't think we need to go into more detail. And the jump. Okay, so I think the last thing I want to look at before jumping into modeling this is those 6 control bits. So let's go, I think that's chapter 2, Boolean arithmetic. Right. The most expensive cube I own. It's one that wouldn't be expensive these days, but when I got it, you know what? I'll show you. I'll show you. In a second though. I'll go grab it. But first we want to figure out these control bits. So here's ALU. Ah, okay. I think this is what we want to use. So we'll paste that in. Okay, I think these might be the 6 control bits in order, and we can verify that against this. So there's the X input, there's the Y input, right? And we can either 0 that or negate that. So let's look at something that has an X and a Y input. So let's look at d plus a. Yeah, just d plus a. So here we're not going to zero. So x is always going to be d, right? So we're not going to zero the d or negate the d or zero the a or negate the a. Um, and what is this f? I don't know, but this is negate the output. So if we're doing d minus a, then to negate the output, what we do is negate x, add a, and then we negate the output. So that's why there's a 1 here, and there's a 1 here, right? This nx is set to on, this no is set to on. And then, yeah. Okay, these are exactly those 6 bits. So we can name all of those flags. F, though, we want to figure out what F does. Oh, here. This is really useful. In fact, it's probably more useful than the one I just pasted. So we'll paste this over. Okay. Presetting the X inputs, presetting the Y input, computing. Oh, the F tells you whether you're doing plus or and. Okay, and then post setting the output. Okay, cool. Yeah, I think that is everything we need to start modeling our machine language. Oh, I'm gonna leave this on screen for a sec. I'll show you that cube. Okay, so way back in the day, in the early days of cubing, you couldn't really get a lot of the fancy cubes you could get today. And someone invented a way to do a 3x4x5. So it's like the very first 3x4x5. And here is a 3x4x5. So this is a shape-shifting cube, right? Like as you, oh, my green screen is hiding a lot of that. But like as you scramble it, the 3 and the 5 layers morph, right? Um, and this wasn't a thing that existed. It wasn't mass produced yet. So I had to get this 3D printed, and it cost like $150 or something. And these days you can just buy this mass produced. You'd probably get this for like 25 bucks nowadays. But I got and it has Tom Z, the name there, because that's the name of the person that designed this mechanism. So back in the day when like you couldn't get this unless you were like 3D printing it, that's when I got this. So I used to be really into it back in the day, but that's like, geez. Uh, oh my God. That's nearly 20 years ago that I got into cubing. Um, Let me think. It's 2026 now. Yeah, in 2006, they had just barely broken like the 20-second barrier. Um, it was really different times. If you could solve it in under 30 seconds, you're one of the top 1,000 in the world. How long did it take me to learn to solve this? Well, this one actually, I had a lot of time to think about it while I was waiting for it in the mail. I used to have a lot of time back in my hands in those days, and I solved it before it actually got to me, actually. So I'd had a 3x4, and I'd already figured out how to solve that. So it was like basically just extending that concept a little bit more. So once I opened the box, I pretty much knew how I was going to solve it. Yeah. And that happened to me with a lot of cubes I bought. I was like, I'd think about it a lot before it arrived, and then by the time it got there, I was ready to solve it. Solution is recursion. Solution is a little bit of just a little bit of group theory. Someday maybe I'll do a lesson on that. If you like YouTube search for me, you can find me giving a talk about Rubik's cubes and group theory. But really, there's only a little bit of information you need to know in order to like start designing your own solutions. And it's I don't know, Google commutators in cubing. And once you learn how to do like a commutator, you can figure out how to work out other commutators on other twisty puzzles. How good am I at the Pyraminx? I was never ever that was never anything I did for speed. Basically, with the Pyraminx, I just fiddle around with it until it's solved. Um, that one's not very hard. Okay, so let's model some instructions. So there's a C instruction. Um, case class C inst. Yeah, let's do that. So it has a few components. Um, I guess there's this A. How are we going to say that? Reference memory? Let me see. What language did they use here? This is the machine language. Um, it's the instruction. Feeds either from the A register or from memory when it's 1. Okay, so we're just going to model this as like a Boolean. So from mem, Boolean. And this means that we're going to dereference the A register and get its address. And maybe, I don't know, like maybe I'll put this into the type itself, and this won't be a Boolean. And then there is the comp. So this is going to be some type comp. For now, let's just do type comp equals int. But we'll model that in more detail later. So there's a dest. Well, let's model a dest and jump. So we have a class dest. And I guess this is basically 3 booleans, right? A, D, and M. Sure. I'm starting to feel like this might actually be a pretty heavyweight way to do this. I'll think of optimizations later, but right now I just want to have a clean model that I can kind of work with. So there's a comp, there's a dest, and there's a jump. So case class jump. What I could do actually, I'm gonna try this with the jump. So like, yes, this is represented as 3 bits, and I could represent this as 3 booleans. I think I just want to get all the specific cases, jump greater than, jump equal, etc. So I might make that an enum. And when you parse it from binary, then we use those 3 bits. So let's do that. Enum jump. So case. I guess we can have a null. So null, jump greater than, jump equals, jump greater than or equal, jump LT, jump NE, jump less equal, and jump unconditionally. Okay, those are the 4 cases. And I guess when we parse that from binary, like we could just do actually, yeah. When you parse from binary, you're basically just doing like the from ordinal. That from we can just basically do jump that from ordinal and pass that along. Maybe at some point we'll have like a specific type for binary words, and that will replace this. Because we specifically have like 16-bit words, right? Yeah, I might do something similar to what I did in Cinecore. In fact, let's do that right now as just a type alias. So type, what are these? These are 16-bit. I'm still just going to represent them as an int, but maybe it's going to be like an opaque type alias. Yeah, we'll just call it binary for now. Or word. So this is just an int for now, and we can change that as we model things more explicitly. And because these are in order, right? Null, null greater than, yeah, the order of those does matter. Like we could make that more explicit later if we want, but just hijacking that from ordinal should do it for us. And from ordinal starts with 0, right? So 0 will be null. There'll be a null jump. Okay, so we have a dest, we have a jump. So a C instruction has a dest and a jump. And a from mem flag. And we're gonna have this extend instruction. Cool. So we'll make instruction sealed trait here. Sealed trait instruction. We have a C instruction and an A instruction. So an A instruction just has a 15-bit number, right? Comp, we're gonna flesh out what comp means later. But we have case class A instruction. And that's just gonna wrap some binary. Last 15 bits. And you know what, let's add some documentation here. So max value of 32767. which is just, how would you write that? 7 FFF? Yeah, in fact, I'd rather write it that way. So the max value is 0x7FFF. And I'm not sure if that's true for binary in general. That's just the biggest positive value we could have for this A instruction. Okay. So this also has 13 bits of the instruction. No, negative. Well, we'll say the range. So 0x0 to 0, 7x7. Okay, yeah, those are possible values there. That also extends instruction. All right. And this binary type, I'm just gonna put that at the front up here. And this destination, do we actually want that as 3 separate flags? I think maybe we kind of do. Like maybe we can switch that out into an enum later. But even if we made an enum, I think we'd want to make A, D, and M each accessible anyway. Right, we might want to enumerate possible dest values. I'm not sure. I'm not sure yet. Um, okay, so comp. So comp, we zero out, we can zero out x, we can negate x, and we'll just make each of those their own flag, I guess. And I like these examples here. This -1 x. Yeah, like this x and y basically just gets replaced with d, and y becomes either a or m. Yeah. So as we're going through this, I'm thinking more and more that the first thing I'll want to do is have a translation from assembly to machine language. And maybe directly assembly. Like I kind of want to go directly from assembly to this representation, but maybe like to binary and then parse the binary. I don't know, I just like the semantics, like having the semantics of like this is the representation we're translating into. Like having that explicit in the code might be nice. But like at some point we also do need to be able to instruct to execute binary. So we'll see. We'll see about that. So this comp, this is gonna be a case. Wait. Yeah, case class comp is gonna have 0x, gate x, 0y, boolean negate y, and then add or subtract. Oh, wait, no, add or and. So if f, then it's add. So we'll do it this way. Add. Otherwise, it is it is anding. Otherwise, it's bitwise and. And then negate out. Negate out is also Boolean. Okay, great. So everything's represented here. And we have all the information we need to like run one of these commands. Cool, I'm happy with that. We do need to have a way to parse this comp though. So let's add a from binary method. So from def from binary. Let me get a comp. So we could just take those 6 bits. I guess we could just construct. Yeah, I'm gonna assume that we're giving. I'm realizing now that binary here is a bit ambiguous. Like, I could be giving it the 6, like just these 6 bits. I think we want to. I think we want binary to mean the 16-bit instruction itself. Yeah, I think that's what I think we do want to mean the 16-bit instruction. So we're gonna do like some masking here or some bit shifting. So we're gonna take what did I call this? We can call this the opcode. So val opcode equals n, and we're gonna shift that to the right by 6 bits. And then we're gonna do this 0x equals we're gonna check if the 6th bit, so like basically 1 0 0 0 0 0. So we could represent that, I guess, as hex, or we could do this. We could do 1 left left 5 bits and n equals 1. Yeah, let's do it that way. And we just do that for all of them. That's always false. Wait. Good catch, good catch. Okay, so we bit shift that over and then we and it. Oh, I think if we're masking this, we want to, no, we do want to and it. Be 0, right? Good call, good call. Thank you. Okay, let's shift the n to the right by 5 bits, and then we'll end that with 1. Cool. I always appreciate that kind of catch. So thank you, Desu. Cool. So 0x is that. And we'll do something similar for all of them. So negate x is going to be shifting over by 4. Do the same thing for y. So this is 3, this is 2. Yeah, we don't need to worry about optimizing this so much. We'll know when we need to. I think I want this to be optimal, like legibility for now. And then same thing for add and negate out. I don't know, I'm not just letting the code formatter do that. So, and you know what? I bet, okay, like this is a silly thing to write here, this n shift 0. But I think all of this is a kind of thing that the compiler can optimize. So I don't think we even need to think about optimizing this really. Um, but that should be correct. Shift it over, gets us that bit. Is that bit 1? Cool. And I think that means for our jump from ordinal does happen to work, I suppose. No. It's not from ordinal n because we just want those 3 bits, those 3 last bits. So we want n and 111. So 0x7, or I mean just 7. Yeah, that takes the last 3 bits. Cool, that's for the jump. And for the dest here, object dest, so def from binary. So n something similar. We want to shift it by 3. Let's get the dest bits. So val dest bits. Oh, hold on. Looking up here, going back up here, we need to be doing this to opcode, not to n. So we're going to take that n, replace it with opcode. And I think the compiler will inline it, but if we inline this val opcode, then that should just be inlined into there by the compiler. And that will all be like constants. Maybe. Okay, here the dest bits are going to be n. We're going to shift to the right 3 bits, right? And then we're going to mask it. We're going to get those next 3 bits by ANDing with 7. Okay, so we're going to get those 3 bits. And I suppose we can just match on dest bits. Isn't there a way to write inline? So I think you can write binary inline in Scala. 0b110. Yeah, okay. So we can do something like this, dest bits match. In fact, that might be nice for things like, say, I don't know, like this, the 7, we can make that 0b111. Right, that's more legible. Okay, so let's match, and if we have 0b000, then I guess we have a dest with false. Okay, I'm realizing at this point I should just get the individual bits. So this first bit represents A, right? So now A equals dest bits. and 0B001. Val, and looking here, D is the middle bit. D equals des bits and 0B010. Val M similarly is just going to be that. And then what we could write here instead is dest ADM. I like to make that explicit in case like I got the three in the wrong order or something, because they have the same type. Okay, so we can parse dest from binary. We can parse jump from binary, from ordinal n, and we'll write it this way. Cool. All right, and now when we're parsing a C instruction, we'll just parse recursively. So object C, so def from binary. Well, there's an n. And now we can just take, what's the first thing? So from mem, let's make this bigger, is going to be n. We're going to shift it to the left. 3 plus 3 plus 6 bits. And then we're going to end that with 1. Or, oh, no, we're going to shift that to the right. One, two, three, four, five. Yes, and then we're going to do, is that equal to 1? Okay, and comp is going to be comp from binary. Let me just pass along that n. This n is a binary, not an int. Dest equals dest from binary. And jump equals jump from binary. Oh, wait. We need an object here. Object jump from binary. Okay. I think that's our model of the language, yeah? And that's our ability to parse that. Okay. Now, I think from this point, I should actually move on to the assembly rather than implementing this, because as we're implementing the assembly, I might realize that I want to change this model here. And it's kind of like a nice smaller piece, like be able to see that translation first. So make sure we understand fully what it is that we are asking the computer to do before we start implementing the computer state changes. Yeah. Well, then time for a new package. So we're going to do an ASM package. Um, okay, so we have a package Nand2Tetris.asm. And I suppose at this point we have to actually look at what the assembly language is. What are the other pieces? Let's go back to the planning. Yeah, let's take a step back and think about the pieces we'll be needing soon. So there is the state. There is a PC state, the machine state. I guess hack. Hack is the name of the computer architecture. Um, yeah, maybe let's at least model the state package first, and then we'll model the assembly. And then on the next stream, we can focus on doing the translations from assembly to machine language and then running that machine language on our state. Okay, so you want to make their, what's it going to be? I suppose hack. It's all technically hack. Like this is hack assembly, hack machine language. Um, I guess we could call this a CPU, the PC. We call it the PC. Um, yeah, we could do a state. It's not technically just a CPU, since it's also like I/O and memory or whatever. It's the computer, but we'll just call it CPU as a shorthand because I don't think we'll model a CPU itself explicitly. So that's our name. So package Nand2Tetris CPU. Um, so what does our state include? Let's look at our README. So there's memory, ROM and RAM both, and they have an explicit size, but I think I might represent as a vector for now. And I think the IO is just represented as memory addresses, as like reserved RAM addresses. But we might model that explicitly separately. I think we might model that separately at a different layer, like in the emulator layer itself, we model the IO. The CPU state is only really aware of addresses. But we do have an A register and a D register. The M is derived, and then we have a program counter. So we do have these three registers. So RAM is going to be, I suppose we have like a binary type here too. We'll do that for now. At some point, we'll think about how we're actually representing that binary and maybe move that to its own package. But for now, we have a vector binary. Let's put ROM first. So we have our read-only memory, also vector binary. And then we have A, which is just, I guess, a binary. We have D, which is binary. And then we have the program counter. And that's all the state. Yeah, and then there's the derived states like FM. This is going to be ROM, or no, RAM at index A. Right. And the current instruction. Like maybe in my model here, I represent data and instructions separately. Like maybe it'll be useful to have that type distinction in here so I don't write bugs. Um, but I don't know. I'll think about that. Right now, it's just all binary. In fact, let me make that as a to-do somewhere. Percent data, instructions with different type tags. Maybe. So M is just going to be data. And then we have current instruction. Def current instruction is going to be ROM A. And this is like the thing that gets parsed. So maybe the binary in the other file, binary is just known as like instruction. I guess I used to type instruction for something else already, but like still, it is an instruction as what we parse in our ML model. Okay, so there's a current instruction. Wait, it's from program counter. Yeah. This is always an address. This can be address or data. This is address. No, this is always just data. RAM, it's always going to be data. Like if we're going to treat it as an address, then we're going to make that an explicit conversion. So at some point, these memory modules, I might wrap that up in its own type where it can accept an address. In fact, let's say this for now. So memory equals a vector of binary, right? And both of these are just memory. Um, always instructions, question mark. Yeah, and if we're ever casting data into like an instruction or address, that'll be an explicit thing. Address or data, like this is always data. And then this is always an address. Okay. Yeah, we'll work with something vaguely like that. And you can sleep on that and change it next time. Represent data instructions in different type tags, also like data instructions and addresses. And until we know what we're representing, it's all just ints right now. Cool. And of course, it'll have some method like def execute instruction. So this is going to be, let me nest my packages here. Wait, why am I not able to? We got a UI bug here where we can't edit that. Okay. Anyway, we're gonna nest our packages here. That way we can just reference this by doing, what was I gonna reference? So we're gonna execute is gonna be like an ml.instruction, and that gives us a new state, right? So this will be a big we execute instruction, we get a new state. And I have half a mind to do that today, but like maybe we save that. Yeah, we leave everything kind of vague and wishy-washy. And we get more concrete with things in the next stream. Okay, in that case, then let's look back at the book and look at the assembly language itself and how we might want to implement that. Um, so specified in two flavors, binary and symbolic. So what we've been implementing is basically the symbolic version, which we're basically parsing from binary so that we can work with a symbolic representation. But this is also technically another symbolic representation. But it's like more capable as a language because assembly at least has like symbols. It has variables. So there's like a symbol table. So that's an important difference when we're assembling, or like between assembly and our symbolic machine language. Um, yeah, specifying these operations in binary is a pain, yada yada. We need a more equivalent symbolic syntax, say load R3 is 7, which would mean, I don't know. I'm going to skip past a bit of this because I want to kind of jump to the specification. Wait, let's look at this visual here. Yeah, let's take a look at this. Hey, fair enough. But good to see. Way too late over here. Over here. Are you across the pond? Because one could say it's way too early. Um, yeah, like 4 a.m. It's 4 a.m. where you are. Good to see you. 3 a.m. Oh my God, yes, go to sleep. All right. So let's look at a program. Yeah, see you around. Okay. So assembly program sum1 to n.asm. Okay, computes r1 equals 1 to whatever r0. R0 is our n. So we set I equals 1. So this is assembly. We have an at I. Wait, so we initialize I equals 1, I guess. M equals 1. Right. But we set it directly in memory. I guess, yeah, we could do it with a virtual register. Oh no, M1 is one of the virtual registers. So we should just be able to say R1, right? Anyway, we set in memory that register to 1. And then at sum equals 0, sum gets to value 17. Because I guess this is the first, I see what's happening. So this is like the first symbol that we see that's not referencing 1 through 16. So it gets the value 17. Or no, I get 16 and 17 because 0 through 15 are special memory values. They are the symbolic registers where we have, I guess, easy access or something. Just add a note about that real quick to our data model here. To do symbolic register values, right? For example, like def R0 is going to be RAM at 0. And if these things are accessed frequently, maybe we optimize. Yeah. And it's just gonna be some like binary value or data value. Okay. So if I is greater than R0, go to stop. So we look at I at the I location. And we set D equals M, right? We copy that over. And we look at R0. And now R0 can be M. So we take the difference. And at stop is going to be our jump location. And depending on the value of D, we jump greater than, right? And the jump will be to stop. And there's a label here for that address. Okay. Okay, this is useful to look at. And then the rest of this, I think, is pretty straightforward. It's just going through all the hoops needed to perform like some summation. And in that loop, jump unconditionally back to the address of loop, which is 4. Wait, why 4? Actually, some of these symbols, local arg, this, that. Yeah, I guess these are like taken by the compiler because these are virtual registers, right? R0 through R15 are always going to reference those. Okay. And this is the binary code that ends up with. Cool. We're going to get to that at some point. And when you do, it'll be cool. Yeah, someone must be managing all these symbols. Screen stands for 16384. Oh, okay. Well, now we know where where the display starts. But I think I'm going to model that at a higher level than this, like at the actual like emulator layer. Okay. The agent that bridges the gap between symbolic code convenient for humans and the binary code understood by computer is the assembler. This is the assembler. Okay, ignore all those details for now, yada yada. And the hack machine language specification. All right, a binary hack program. Sequence of text lines, each consisting of 16 bits. Starts with a 0, it's an A instruction, otherwise a C instruction. Cool, and we're basically alternating constantly between A and C instructions, right? This becomes an A, C, yeah. Otherwise, it represents a C. Great. An assembly hack program is a sequence of text lines, each being an assembly instruction, a label declaration, or a comment. So these labels are important because those will each get their own address. And I wonder if this label, does it correspond to like line number? So like we're jumping to loop, for example. Loop is at line 4. Yeah, we're jumping back to like line 4 in this thing. And stop, for example, is 18. And that goes here. Yeah, and I don't think it's not going to match up one-to-one with the line numbers in the assembly here. Oh, right. Like some of these are multi-line things, right, with this comment and whatnot. Stop is supposed to be 18. Does each line of assembly translate into exactly one line of machine code? Like maybe. I think so. Yeah. I feel like there's probably an edge case somewhere, but for now we can assume that's roughly one-to-one-ish. Assembly instructions, label declaration, or a comment, sure. Oh, and they brought this up again. I'm pretty sure they showed this exact same figure in chapter 5. Anyway, symbols and hack assembly programs fall into 3 categories: predefined symbols, label symbols, and variable symbols. Okay, so we'll need to be able to modify the different symbols, label symbols, and okay, so the predefined are R0 through R15 for the virtual registers. SP, LCL, arg this, that, stand for 0, 1, 2, 3, 4. Oh, okay. Stack pointer, local, arg this, that. Okay, I guess that'll be important for at the like compiler levels above later. Let's just put that into our spec real quick. So we have maybe we want this sp local arg this that. Maybe those will matter there. And screen and keyboard 13384. And keyboard is 24576. 13384. I just want to translate that directly to two hex string. Oh, that's not a very much more useful hex string. Did I get the right value? 16384. Oh yeah, that makes more sense. That's like halfway. Um, okay. I like using numbers like that better. So let's do that. 2x 4000. And 24576. 24576. 6000. Good to know. Okay, so basically our usable memory then is like um, everything before 4,000, which isn't a lot, I don't think. And these are in RAM, right? RAM. Okay, yeah, these are all addresses in hack RAM. Can remove that question mark, I suppose. Okay, label symbols. Pseudo instruction XXX defines the symbol XXX refer to location in hack ROM holding the next instruction in the program. Okay, label symbol. So, right, this all gets loaded into the ROM, and this basically says whatever the address is of this next thing. Create label symbols and a variable symbol. Any symbol XXX appearing in an assembly program that is not predefined and not defined elsewhere by a label declaration is treated as a variable. Okay, so variables are mapped to consecutive RAM locations. Okay, predefined labels and variables. Now, the first time I went through this, I would have gone from the text of the assembly, probably directly to outputting machine code. So directly from that to binary. And this time around, I don't want to do that. I do want to have like an intermediate model. So I'm going to model the assembly. And why am I doing that? Mm, I mean, I think it's what you might want to do with a more complicated assembly language. So like this one's supposed to be easy intentionally. Um, but if you want to do more complicated things, and if you want to do like transformations on the assembly itself, I think it'll be a lot easier to do if we have a model of the assembly rather than just text. I don't want to just transform one text into another text, right? And if we want to do like any other kind of representations, I want to have semantics here and not just text. So I'm going to do it in a more roundabout way than I would have done it in the past, which means like more work, more code. Um, it'll take a little bit longer, but I think it might be worthwhile. Okay, so those are those symbols, three categories: predefined, labels, and variable symbols. Now, what's this? A symbol can be any sequence of letters. Okay, we're getting into parsing, right? A constant may only appear in A instructions with the form at whatever. Cool. I think before the next stream, I'm going to choose a parser combinator library, maybe. Like parsing this isn't a thing that needs a parser combinator library. Like it's intentionally designed to be like simple enough to just do a hand rolled parser. But maybe I'm gonna think on whether I want to use a parser or roll my own here. White space, leading in white space is empty and ignored. Okay, sure. Um, I just do like semantics and parser combinator, so I might do that just to have this whole thing being more semantic. And case conventions, all assembly mnemonics must be written in uppercase. A+1, jump equal, etc. Okay. This completes the machine language specification. That's not the whole specification because there are commands like a equals a plus d or something like that, right? Oh, interestingly, some of them are not representable. So if we go back here to the dest, so package and ML, you can have like a multiple destination, right? Like all of these can be true. Like you're writing to the data register and to memory. Which how would you say that in assembly, right? That would be like I don't know. Let's say, you're setting the values to like whatever is an A. So you could say like D equals A. Um, but you would say like D or M, like on the same line, and M equals A of some sort. So there are machine language things that could happen that you can't really represent in the assembly. Okay, this might be a case for extending the assembly itself. I just don't know like what a sensible way to do that would be. But interesting to note. So like some of these things will never really get used. So in practice, destination is really just one of these three, even though you could use those 3 bits in different ways. So maybe simplify, like maybe I'll simplify this to 3 possible destinations rather than 8. Rather than 8. And sometimes there's no destination. Um, so or null dest, right? Value is not stored. Assembly to binary instructions. For each assembly instruction, the assembler parses the instructions into its underlying fields. For each field, generate the corresponding bit code as specified in figure 6.2 right here. So you could write something like D equals that plus that, whatever, and then it's semicolon jump. Oh, here's the symbolic. Zoom on that. So here we have the symbolic dest equals comp semicolon jump. This is assembly. That's what an assembly instruction looks like. So dest is optional. Comp is a computation. The computation is going to look something like one of these. It's going to be like an and or an or a sub. That might have 1 argument or 2 arguments. Are these all the possible computations that we care about in assembly? Because there are many more possible computations. If we like flip all of these, they just don't necessarily have a meaning, right? Like you flip any of these bits, it'll make the computer do something. And that something might not really make sense. Oh, here, dest. I guess you could say AM equals whatever. So same here, say AM equals or AMD equals A. Or well, I don't know, MD equals A. So set M to A and set D to A. Okay, so maybe we won't simplify it. Comp is mandatory. If dest is empty, the equal is omitted. If jup is empty, the semicolon is omitted. So I think our symbolic is just going to be one-to-one with assembly, which is to say, like, we can translate it from assembly into our model, and vice versa. It only has one way to print. Yeah. Okay. But what I'm still missing from here is what computations are possible. It tells us about the symbols. Um, hack program is a sequence of text lines, each being an assembly instruction, a label declaration, or a comment. An assembly instruction. Right. 6.2. Yeah, assembly instruction. A label declaration or a comment. And an assembly instruction can use symbols. Right, so we're not just doing like D equals whatever plus whatever, because sometimes we have things like, well, where do we use symbols here? At I. I guess the symbols only ever really refer to memory. So an A instruction could use a hard-coded value or a symbol of some sort. Okay. So, a label declaration or a comment. An A instruction can use the symbols. The label declaration could also use symbols. And handling symbols, handling instructions. For each assembly instruction, remember, the assembler parses the instructions into its underlying fields. For each field generates corresponding bit code. Yeah. And if the instruction contains a symbolic reference, resolve the symbol into its numeric value. Okay. This is making me want to. So we'll have some sort of symbol. I don't know. Here. So like, there's going to be a comp, for example. And in this comp, it's going to be represented as something like D minus M or whatever. And I think I do want to directly translate that. So that's what we would translate into binary. I think I also want just directly translate that into comp, um, like the comp type that we have. And we could stay out of binary space for now. And I guess if we have two different paths from assembly to the machine language representation, then we could test them against each other. I should try Linux. I am using Linux. I've tried Linux plenty. I've I used Arch for like over a decade. And why am I using Windows now? Because that's WSL. Like, there's things I miss, but there's things I don't miss. Having to do like so much maintenance on your own system. And WSL is pretty nice. I also like the compatibility with like all the tools and streaming, whatever. I think streaming is nicer on Windows. Like, you can always figure out how to do things in Linux. I think this is technically, uh, I think this is between, um, oh, I don't know. I don't know what we are. I think this is Ubuntu or Debian. It's probably Ubuntu. I still use Linux in prod at work, and I use it via WSL here at home. That's my daily driver OS. I don't use it that way anymore. Um, anyway, you get me a little sidetracked. I think I can, before the end of the stream, I can do a quick and dirty model of the assembly. And then next stream is where we start translating these from one to the other. So initialization, the assembler creates a symbol table. Sure, we'll need a symbol table. First pass, the assembler goes through the entire assembly program, line by line. Um, keeping track of the line number, right? Because we'll need that for when we declare labels and use symbols. This pass results in adding to the symbol table all the program's label symbols. Great. And second pass, we go through again and parse each line as follows. Each time an A instruction with a symbolic reference is countered, the assembler looks up at that in the symbol table. Right. So we can pass over the assembly and try to transform it so it's not using symbols and it's just using constants. And that constant has like a one-to-one translation with machine language, or at least not one-to-one, like it's like onto. It's not like a full bijection, but a one-way translation into machine language where it's straightforward. Okay, yeah, that makes sense. The symbol is found, the assembler replaces it with its numeric value, yada yada. Um, cool. And implementation, developing a basic assembler, parser. We can figure out parser ourselves. Um, oh yeah, like this. I don't want it to give me a parser API. Like I will either just use a parser combinator or do like a hand roll, whatever in my brain. Maybe I'll do a hand roll. It might be more in the spirit of things to do a hand roll parser, and it's not very hard. Comp is 7 bits as a string. Interesting. I think we modeled comp a little bit differently here. We modeled comp as like 6 bits essentially, and from mem as like its own flag here. But maybe from mem should be part of comp. From mem here. We'll leave that as a note, design note. Maybe we change that. And at some point, I think I'll do a TDD approach next stream where I'll use this model to write some tests of things we expect to happen. Maybe I'll translate some examples directly from the book. Um, yeah. And the hack assembler, and yada yada. You don't need any of this. Oh, look at this. Right. Yeah. So they include software here. like this is part of what I want to do with this run through is like software like this. I want to implement basically my own version of these tools. So this version I'll probably just implement in software. I won't make a UI or anything. But the part where I want to make my own UI is going to be in like the emulator itself that shows the screen and like the keyboard and it takes a keyboard input, stuff like that. Um, anyway, we have what we need. Let's model assembly, a rough, quick and dirty version. So assembly package. Okay. Um, so we have an assembly instruction. I want to use the same terms we were using. So there was, you go back a few pages here. Uh, where is it? Okay, we have text lines. Uh, each assembling, okay, each line represents an assembly instruction, label decoration, or a comment. Okay, we'll call them assembly instructions because we have something called instruction already in a different package. We'll figure out, we'll declobber all the names in the future, but for now we have like an assembly instruction. And then we have two types of instructions. So we have an A instruction, and this thing has one parameter. It's like either a symbol or a constant. So type constant, just be an int for now. We'll add validation and whatever refinements to that later. And there's a type symbol. It's just gonna be a string. So this has an arg. I know they keep calling it xxx. We'll just do that. xxx. This is either a constant or a symbol. Where a symbol might mean a few things. There's a few types of symbols. So there's a C instruction. So like this instruction. And then case class C instruction. I'm just going to type inst. Try to type the whole thing. So a C instruction has a few parts. Let's zoom in on that. Okay. The constant, by the way, it's going to have a range. So it's going to be 0 up to 0x 7fff. To do validate. It'll be fun to go through and refine those types later. But right now we have just the next 15 minutes or so to get through these. So let's get through them. There's a dest option of, I guess it's a set of registers or a set of, it's like one of A, D, and M. It's kind of identical to BH to this dest. Or at least it has like a direct one-to-one translation. Uh, let's do let's do this. Enum dest is going to be A, D, and M. And instead of options, it's just going to be a set of dest. Jump's also going to be optional. If jump is empty, it's well, I mean, it's not really also optional. Like it's always there, but sometimes the thing that is there is 0, 0, 0, right? And that's null, or like the empty set, if you will. So like we can do the same thing here. Yeah, let's do it that way for now. So there's a jump. It's optional, but what we're going to treat that is so if null, don't show in string, right? That part after the semicolon just doesn't appear. And then comp. Comp is the fun type here. Because this is where the semantics really diverge from the machine language. So we have I guess we have two different types of comps. So there's like add or subtract. Well, it's usually like D and A or it's never A and M. So it's like either D and A or D and M. So I kind of want to make that explicit. Hey, Alex, it's been a while. Yeah, it's been a hot minute. Good to see you. Um, hmm, I'm not sure how generic to make this. So we know we have add, we have subtract. And the right side of that add can be 1 or A or D. Wait. Yeah, 1 or A or D. Here's the thing though, like this one, you could sort of say that the left side is D. You could say in all of these that the left side is D. The left side could be 0, right? So left side is 0, or I guess -1. No, 0 or D. Right side is 0 or D or no, or M or A. Like what's going on here? 1, 1, 1. Like in the machine, we're saying like we zero it out and then we negate it. And we are adding, right? This means add. Here. If F, then we're adding, right? So like when we do this one command, or yeah, when our comp is just 1, we're taking that 0, we're negating it. we're adding it to another. So like we're adding -1 and -1, and then we're negating that. What happens when you add -1 and -1? That like that overflows. And then you negate the output. Hold up, hold up. So we take a 0, and then like we not that, so like 0, we not that to get -1, right? Like so two binary string. Wait, two binary string. Yeah. So we take like 0 plus 0, and that happens. I mean, when we negate that, right? Because this is 2. This is -2. And oh, right, two's complement. So like when negate -2, when you bitwise negate -2, then you get 1. Now when we're parsing this, like back and forth, like I don't want to represent that as like arg1 is always going to be D, for example, here, right? But I don't want to say that arg1 is always going to be on the left side, because then we have to parse slash write stuff like -D plus A. And I do like that they how they have it here, where it's just that, and the things you can do to it are +1 plus whatever. Oh, we're gonna have a seal trait because our two comps are essentially maybe three comps. Seal trait comp. We have add and we have subtract. We have and we have or. Yeah, I want to keep all of this stuff here hidden. So the things we can have, case class add left is going to be a register. We have an arg. So type arg, let's just default that to string for now, and we'll fix it. So left, right, arg. We have and. We have subtract. And we have or. I don't like what we're listening to. I'm going to change that real quick. Okay, add and sub and or. And like this here, like this is technically like 0 minus A. Like what's going on here, we're taking like the left register, we're zeroing it out. And we are also negating it. So we have -1 plus. Okay, this is -1 plus A, and we negate that whole thing, which means we get A -1. Hold up. No. Because he bitwise negate it. He bitwise negate it. So that just does become -A. So we could model unary operations explicitly. So case class neg. And the arg here, so the arg here, when we negate, can be A, D, or M, or constants. A, D, M. Let's make this common so it's not confusing. And 0, 1, -1. Let me pause here for a second and explain why I'm overthinking this. I'm torn between two poles of how to represent this. And on one pole, we just explicitly list out all these possible operations, right? But these operations can be written in terms of others, right? This -1 could be conceptually something like 0, -1, or whatever. But we don't want to go so far around that we're basically just recreating the machine language opcode. Because what I want to have is an easy translation between the assembly that we're reading and writing and this. And in fact, I might want to write my assembly as a DSL. So I want to be able to write, in Scala, I could write something like dest.d equals, and you'd give equals a value here, or we can dot set to maybe not dest dot, or yeah, register.a plus register.b, right? Or register.b. Or we should be able to write +1. So that's my ultimate goal there, is to be able to write something like that. And really, I think there's a way to override what equals does as a function. Right. I want to be able to write something like that as assembly and do something like assembler.compile, and then this is the list of instructions. Right. I think that can be my hard mode version of this, is not just doing an assembler from text, but an assembly DSL, something like that. Something for me to sleep on. Right. And then we can do to binary or whatever. So that's my goal. But for now, let's just get all these computations down and we can refine it later. So things we can do, we can negate. Maybe we have a constant case class, constant, or rather, these will extend comp. Extends comp. And then seal trait const. Or actually, we might have an enum. Let's make a seal trait for now. So const extends comp, and then we have inside of comps, we have case object 0, 1, -1. The three possible constants we can use here. Not to be confused with this constant we were doing here, where an A instruction can take a constant or symbol. So case objects, we have 0, 1, and then we have -1. Something like that. And what is an arg? An arg is either a register or a constant. Register or a 1. I guess we can have a neg. We can have just 0 or 1. We don't have to have -1. Because we can just neg arg, where that's a constant. Or const, I guess. Yeah. Something like that. There's also not. So there's negate, there's also not. And in this case, it's only going to be args, which in this case are like registers. And when you're adding something, the left is always going to be like some register. The right is going to be a register or a constant, I suppose. And there's some like validity checks to do. A plus M, etc. is not possible. So it's going to be D and either A or M, depending on this flag here, this A flag. So that's either going to be either a validation step or not presentable. My instinct, I always prefer to make things not representable at all in the first place. But if that is too messy to do, then we will just make it a separate validation step. So type, let's say there's a register. I'll say that's a string for now. The left side is always going to be a register of all of these. Right's going to be like a register or a const. Yeah, and then there's negate, and there is not. And we can negate an arg or a const. Actually, we can negate a register or a const. You can only not a register. Okay, that makes sense. That's a little bit more constrained. Oh my God, CM Griffin, you're rating right now? I'm about to call it in 5 minutes. Welcome, welcome. How is it going? Um, I suppose I at least owe you all an explanation of what's going on here. So yeah, tell me how your stream went. In the meantime, so I'm doing Nand2Tetris. This is something I've done. I did this like over a decade ago. So this is kind of like my new game class on Nand2Tetris, and I'm doing it again, and I'm doing it. I'm giving myself more space to like tinker with it and explore. And importantly, I'm writing a whole emulator. So for the whole computer platform, the original Nand2Tetris, you're basically given NAND gates to start, right? And then you wire those together. You build other types of gates. You build circuits for like memory, for an ALU, for like how to add and things. And then you build like a whole CPU with a that accepts a machine language, right? So you're building this all in like a hardware definition language, which maps together like where the wires go to what chip and whatnot. And it walks you through building this full computer platform. It's called the Hack computer architecture. And on top of that, you write an assembler, an assembly language that runs on this, and then like a VM translator, and then a compiler for a language that runs on that VM, etc. Um, all the way to the point where you can write a game like Tetris and have it run on architecture you understand all the way down through the VM, through the bits to the actual circuits itself. Um, so that's what I'm doing. And in this revisit, and in the last few weeks, I went through a kind of warm up doing the circuits version of this. But I'm running a full emulator. I'm gonna have this run in the browser with like the visuals and display, etc. That's not stuff that's like part of the original project. Um, and then I'm gonna do other cool stuff with it. So I'm gonna try and use like more sophisticated techniques or whatnot, and have like different representations I could play with and transform and do like debug stuff on. So that's the goal. And this is the first stream of that. So this has been kind of like a planning exploration session. We've been going back through the book, through the spec. We've gone through the spec for the machine language itself, um, through the spec for the state of the machine itself. So it has like ROM, RAM, a couple of registers, it has a bunch of virtual registers. Um, and then just now, well, here's the machine language spec. So this is like kind of a direct one-to-one translation of the binary and what the binary itself means. Like, are we negating the X argument, or etc., or like, where is this going to be stored? And are we going to jump after running this instruction? And just now, I was going through like a quick and dirty rough model of the assembly language itself, um, with half an intent to implement the assembly as like a DSL within Scala here. But this is what's going to translate down into machine code, and the machine code is going to run on this computer architecture and do like all the state transitions. And so I've just finished doing a rough model of the types of instructions we have at the assembly level. Uh, these are things like, D equals D plus A or whatever, or creating a label, or things like that. And I'm gonna leave as a to do. There are a few types of symbols we have. So an assembly instruction. Yeah, I need to expand the symbol type because there are some like built-in symbols and there are some symbols that you can define yourself. And those end up in the symbol table that tells you like what memory address those symbols are pointing to or your variables. But yeah, this is about where we're calling it. Let me just look at what else I want to add from here. And I'm curious if anyone here's done Nand2Tetris before. Like, it was one of my favorite experiences as like a beginner programmer. I would call it formative even, but highly recommend it. It's based on this book, The Elements of Computing Systems. It has a web page itself, like Nand2Tetris, where like you can do part one of this for free, essentially, and then you get the book if you want to do part two. So part one being everything up to the assembler, and part two is the virtual machine and compiler and operating system that you build on top of that. Yeah, so I'll just drop links for people that are interested in this kind of stuff. Um, yeah. Okay, so symbols in the assembly language. There are three different kinds. There are predefined symbols, label symbols, um, and variable symbols. Um, these are our operations. A C instruction. So there are two types of instructions. There are A instructions, which basically let you inject a constant or an address. Fair enough. Yeah, enjoy your meal. Thanks for a raid. Okay, so we have A instructions and we have C instructions. Um, C instructions are like the actual computation. So for every C instruction, let me just point it out here, there is a destination where that's being stored, either like a register or like in memory. The computation itself is something like AND or add or subtract. And then there is a jump location. We've defined jump, or not a jump location, rather, but like a jump instruction. You would just jump to whatever is currently in the A register. Um, and the symbol. Let's flesh out what a symbol means real quick. So we have sealed trait symbol, and then we have three types of symbols. Predefined. Um, so we have a enum predef symbol. Or you know what? I might do it this way because there are a few different kinds of predefined symbols, and some of them are overlapping. Um, because there are these R0 through R15, which are for the virtual registers. Um, you know what? Let's not get fancy with the types right now. Let's just get it down. Just write all of these down in turn. So sealed trait, predef symbol. And then we'll just make a bunch of case objects. So R0, R um, virtual register. This is a place where I kind of want Copilot to come in, just autofill this. We'll do it this way. So we'll copy paste. I'm sure there's like macro and VS Code for this, but I haven't learned that yet. So we have until 15. So well, there's a register 0. Okay. Um, we're actually gonna do it this way. We can put that all in one line. Yeah, that works. And then there are SP local arg this that. Okay, so local arg this and that. If anyone's able to think ahead, they already know I'm going to have to change this, but I just want to get it down, written down in the code. And then screen and keyboard. So all these predef symbols do have like a meaning. Yeah, I'll think about how to model that. So there's also screen, which is 0x4000, and keyboard, which is 0x6000. Or KBD, rather. KBD. And then there is case class label. So name string, this also extends symbol. And a variable symbol. Any symbol XXX appearing in an assembly program that's not predefined and not defined elsewhere by a label is a variable. So case class, we'll just call it a variable, name string. And it doesn't get assigned a value yet, because we don't know what value it will have until we construct the symbol table. So this also extends symbol. Okay. So we have that all kind of in place. And the symbols are only ever used in A instructions, which take either a constant or a symbol. Constant for now being an int, but we might do something with that type alias and give it some constraints. Anyway, we are past my time, so you kind of get the idea of where this is going. So thank you, Raiders, for sticking around a bit, and thank you everyone who's been here. We should find someone else to pass the raid on to. And yeah, if you want to see where this goes, I'm doing this weekly every Tuesday at 8 p.m. Eastern. So next week we'll basically be taking the pieces that we've sort of roughly modeled, so the assembly, the machine language representation on the state, and start wiring them together. So like wire turning assembly into machine language, and wire executing machine language instructions on the state to do some like state transformations. So we'll do some number of those pieces next Tuesday at 8 p.m. And yeah, let's find a raid. If anyone has recommendations, if there is someone doing some sort of low-level assembly-ish thing, that'd be an appropriate place to pass the torch. What do we have? Let's see. Or who do I know? I don't imagine anyone's actually doing like anything to do with assembly, right? No, of course, it's just me. Um, anyone doing like compilers or something like that? Compiler, virtual machines, emulators. Maybe someone's doing like an emulator of some sort. Game Jam, making an RPG. Who am I following that I know here? Yato. Yato's doing an idle game. Idle game gets a few tweaks. Retro dungeon crawling roguelike RPG indie game dev. That sounds interesting. Um, I don't know what the new project is here. Doing some sort of roguelike seems fun. Let's go here. All right. Let's say goodnight. Yeah, thank you. Have a good night. Thanks for stopping by, all of you.